So just like we had with two variable systems, we can have three variable systems where we have no solution or where we have infinite solutions. So I wanted to demonstrate an example of each of those here today. Now, I'm going to approach this the same way that I did with the other three variable system problems. I have to find a variable that I'm going to get rid of twice. Now in this case, none of them are super easy, but none of them are impossible either. But I'm going to go ahead and target the x's for elimination. I should be able to get rid of those twice without too much trouble. So I'm going to start and I'm going to take the top and bottom equation and combine those in a way to make the x's disappear. Well, to make that happen, I'm going to have to multiply that top equation, the top one, by 2, because I want to have the x's have the same coefficient. So I'm going to multiply that top equation by 2, and so that's going to lead me to 2x minus 4y plus 2z equals 8. Got to remember to multiply everything in that equation by 2. And then the bottom equation, I'm just going to copy as is. So I'm going to have 2x plus y plus 4z equals 2. So I don't have to do anything to that one. And so now I'm going to subtract these two equations, and that will get rid of the x's. And so if I do that, indeed the x's go away. Now again, with our subtraction, we have to be careful. It's negative 4y minus y, so negative 4 minus 1 becomes negative 5y. 2z minus 4z gives me negative 2z. And then finally, 8 minus 2 gives me 6. So far, this could have been in our previous notes. Now, I'm going to take the top two equations and combine those. Now again, in order to get the same coefficient in front of both the x's, I'm going to have to multiply that top equation, but this time I'm going to have to multiply that top equation by 3. So times 3. So I get 3x minus 6y plus 3z equals 12. So again, I just multiplied every part of that equation by 3. And then I'm just going to copy that middle equation down. So I'm going to have 3x minus 6y plus 3z equals 7. And so I think we can see where this is headed. I need to subtract these equations to get the x's to disappear, but if we look at the y's and if we look at the z's, they're all the same. 3x minus 3x is gone. Negative 6y minus a negative 6y becomes negative 6y plus 6y. That's gone. 3z minus 3z is gone. So on this side of the equation, I have nothing. I have 0. On the other side, however, I don't have 0. I have 12 minus 7, which is 5. Now 0 does not equal 5. That is a false statement. That is not true. So in these circumstances where all of our variables disappear at some point in our solving process, and we're left with a false statement like the one that we see here, 0 equals 5, that is an indication that this system of equations is broken somehow, and so therefore we have no solution. There is no ordered triple that we can plug into all three equations and have it make a true statement. Now we can also have circumstances where we end up with infinite solutions, where there's not just one ordered triple, but there's an endless number of them. Now we had a mechanism for dealing with that. With the two variable systems, this is going to be slightly different. It's going to involve a little bit more out of us, unfortunately, so we're going to have to hang in there a little bit. But at the outset, we're going to approach it the same way that we have all the others, where we're going to target one variable for elimination. And so in this case, I'm again going ahead and go with the x's. None of them are terribly great. X is okay, z is okay, y is pretty bad. So I would go with the x's again here. So I'm going to start off and I'm going to combine the top two equations. So I'm going to be able to just copy the top equation, but I'm going to have to multiply the bottom equation by 3. So I'm going to go ahead and do that. So I've got the top equation is 3x minus 3y plus 6z equals 6. And then this one, I'm going to have to do the second equation times, let's give ourselves a little bit more room there. So I'm going to have to multiply the second equation times 3. So I'm going to get 3x plus 6y minus 3z equals 15. And now I can see the x's have a match, so I'm going to subtract these two equations. And so when I do that, the x's indeed disappear. We have to be very cautious with our positive and negative signs here. So I've got negative 3y minus 6y. That gives me negative 9y. Then I have 6z minus negative 3z, so that becomes 6z plus 3z, so plus 9z. And then finally 6 minus 15 is negative 9. So we've combined the top two equations. Now I'm going to combine the bottom two equations. But again, I'm going to have to multiply that middle equation, the middle one, by 5 in order to get the x's to match up. So I'm going to go ahead and do that. So the second equation times 5. So I'm going to have 5x plus 10y minus 5z equals 25. And then I can just copy down the bottom equation, 5x minus 8y plus 13z equals 7. And now once more I'm going to have to subtract these equations. And so if we subtract those, the x's go. 10 minus negative 8 becomes 10 plus 8, so we get 18y. Same thing with the subtraction once more. Negative 5 minus 13, so negative 5 minus 13 is going to give us negative 18z, and then 25 minus 7 gives us 18. So now I've got my two equations. I've got this one here that involves just y and z, and this one here that involves just y and z. And so now I have to get rid of one of the variables. I have to combine these to get rid of one of the variables. So if we focus in on the y's, let's say, and so we can see that I could multiply the top equation here times 2, and then I'll get a match, even though there'll be different positive and negative signs. That's fine. That just means that we'll have to add the equation. Well, if I do that, I get negative 18y, so I'm multiplying this guy by 2, negative 18y plus 18z equals negative 18. I have to multiply everything by 2. And then I can just copy down this equation. So we have 18y minus 18z equals 18. And so hopefully what we see is happening here is when I go to add these two equations, everything, negative 18y plus 18y, gone. 18z plus negative 18z, also gone. So on this side I'm getting 0, but unlike the last example where we got a nonsense statement, here negative 18 plus 18, I get 0 on the other side as well. And so this tells me that I have infinite solutions to this system of equations. But unfortunately, it's not as easy as how we handled the two variable systems, where we could just write x comma y and then one of the two equations. We can't just write x, y, z and then one of the three equations. It's just a more nuanced answer that we need to put down. So this is the technique that we're going to have to use for this. It's a little bit burdensome, but hopefully it'll make sense by the time we get to the end of it. So what we're going to do is we're going to say that z is equal to a. We're going to do this every single time. We're going to say that z is equal to a, where a is just going to represent any number, negative, positive, fraction, decimal, 0, it's anything. So we're going to say z equals a, and then we're going to come up with expressions for y and for x in terms of this mystery number a. And so then this will give us the relationship between the three variables that will work for all three equations. So I'm going to take this z equals a, and I'm going to plug it into this equation here. I could have used this one down here as well. It doesn't matter, but the one in green here has smaller numbers, so I'm going to go with it. So I'm going to replace z with a in that equation, and then I'm going to figure out an expression for y in terms of a. So I'm going to say negative 9y plus 9a equals negative 9. And now I'm going to solve for y. I'm going to get y by itself and There's going to be an a in the expression when I'm done. So the first thing I need to do, I have to isolate y, so I have to subtract this 9a. This is awkward, but we'll get there. So I've got negative 9y equals negative 9 minus 9a. And now, to get y by itself, I need to divide by negative 9, and so I'm going to divide everything by that negative 9. So that goes. So I've got y equals, now negative 9 divided by negative 9 is just 1, and then negative 9a divided by negative 9 is going to be positive a. So we start with, when z is a, what this is telling us is y is 1 bigger than that. So if z is 5, that means y is going to be 5 plus 1, it's going to be 6. If z is negative 8, y is going to be negative 8 plus 1, so negative 7. So this is just telling us the relationship between the numbers that are going to take the place of z, the numbers that are going to replace the y, and now we need to figure out what the x is going to be. So I need to take this, and then plug it into any one of the three equations, original equations. And I'm going to pick the one in the middle because the x is kind of the simplest, since that's the variable I'm going to solve for. So that's what I'm going to do, and I'm going to squeeze it in right here in the middle here in green. So I'm going to have x plus 2 times, now in place of y, I'm going to put this 1 plus a, and then minus z, but in place of z, I'm going to put a, and then equals 5. So the idea here is I'm going to get an expression for x that involves a. And so this is going to show me how these three variables, x, y, and z, all relate to each other. So I've got a little bit of work to do here. I've got to distribute the 2. So I've got x plus 2 plus 2a minus a, having a little lag here, my apologies, equals 5. I'm going to gather like terms here. So I've got x, and then I've got plus 2, and then I've got 2a minus a is going to give me just a equals 5. And now I've got to work on just getting that x all by itself. So I'm going to subtract 2 from both sides first. So I've got x plus a equals 3. Believe it or not, that's a 3. And then I'm going to subtract a from both sides as well to get x by itself. So I have x equals 3 minus a. And so then taken together, these three things, z equals a, y equals 1 plus a, and then x equals 3 minus a, is the relationship between these three variables. So my final answer, the way we'll write it, is as an ordered triple using these three expressions. So I've got 3 minus a is x, 1 plus a is y, and then just regular old a is z. And so then I can plug in any number I want for a. So I could plug in 0, so that would mean that 3, 1, 0 would work in all three equations. I could plug in 1 for a. That would mean that 2, 2, 1 would work in all three of those equations. So I can plug in any number I want for a, and that will give into these three expressions for a, and that will tell me what an ordered triple that works in each of these equations. If this is tough, hang in there, do your best on the homework, and we'll go through this in a little bit more detail in our next session.